Hello everyone, welcome back to another video. Let's take a look at the work energy power questions from the June 2024 exam. Question 5.1 reads, an object of mass 20 kilograms released from rest at point P 5 meters above the ground. It slides down the track and comes to rest at point S, which is 4 meters above the ground. The curved section PQ is frictionless. The horizontal section QR is 10 meters long and is also frictionless. RS is inclined at an unknown angle and is rough. The frictional force, a non-conservative force, between the surface and the object is 20 newtons. Pause the video now if you'd like to give it a go. We're going to go through the answers in 3, 2, 1. 5.1.1 state the principle of conservation of mechanical energy in words. We won't go too much into detail here because of course you have the memos and you have the definition list, but basically this states that the total mechanical energy in an isolated system is conserved. So 5.1.2 is mechanical energy conserved as the object slides from P to S. Okay, so they may be trying to trick you here, but we need to understand what conservative and non-conservative forces are. So conservative forces, or some examples of conservative forces, is a force maybe like gravity or electric fields. There are others. I will link the video in the top right corner. Non-conservative forces are examples like friction, the force applied. Okay? And what we need to know here is that in the absence of non-conservative forces, so meaning when they're not there, mechanical energy is conserved. Okay, so I'm going to use a highlighter and highlight the sections. So P and Q, they told us, is frictionless. So there's no non-conservative forces there. QR, frictionless, no non-conservative forces there. But RS has friction. So in other words, we can basically what we're trying to say here is that from Q to R to S, so this whole section here, mechanical energy is conserved. But from R to S, it's not conserved. So the question is asking from P to S, so this entire thing, is mechanical energy conserved? The answer is no. All right, let's move on. The kinetic energy of the object at point Q is equal to that at point R. Use energy principles. So energy principles is mechanical energy. To determine the speed of an object at point R. Okay, so let's look at the information that we have. So we know mechanical energy is going to be the same, right? We know that the mechanical energy at point P is going to equal the mechanical energy at point Q, and that's going to equal the mechanical energy at point R. So we can work out the mechanical energy at P, and we can get the velocity at Q. And if we got the velocity at Q, then we'll know the velocity at R. So let's go through that and I'll show you how it works. So we'll start off by saying the mechanical energy at P is equal to the mechanical energy at Q. Okay? So mgh plus half mv squared is equal to mgh plus half mv squared. Point Q is on the ground, so h is 0, that's going to be 0. At the top at point P, the object is released from rest, meaning v is 0. So that's going to be 0. So we're left with mgh equals half mv squared. Let's substitute and solve. So the mass of the object is 20, gravity is 9,8, the height is 5. That's equal to half, 10, and then v squared. We can solve for the velocity at q. The velocity at q is going to work out to be 9,90 meters per second. Now, we must understand something. If you look at QR is frictionless. So in other words, there's nothing to slow down this object. So if the object has a velocity of 9,9 here, it's going to have a velocity of 9,9 there as well. So you could think of it like that, or you could think of it in the statement they've given us the kinetic energy of the object is equal. So you could think maybe since the object is not changing, its mass is not changing, the velocity must be the same for the kinetic energy to be the same. Whichever way you choose to think of it, that both work. Okay, question 5.1.4. Explain the term non-conservative force. Again, definition, you have access to that. I'm not going to go through that. Now, last question, 5.1.5, calculate the magnitude of the angle theta. Now, there are a few equations that you can use to calculate work for this section. So one of the equations are W net is equal to delta EK. The other equation is WNC is equal to delta EP plus delta EK. Now, since we've been given the value for friction, right, and we know friction is a non-conservative force, it would make sense to use this equation instead of this equation. All right, so let's start with this equation. We're going to say WNC is equal to delta EP plus delta EK. So the work done by the non-conservative force, when the object is moving up the slope, the non-conservative force is friction. There's no force applied. So this could easily just be the work done by friction is going to be delta EP plus delta EK. Let's substitute now. We know that work, let's write it, work is equal to the force multiplied by the displacement multiplied by cos theta. So it's going to be friction times delta x times cos theta. And this is going to be mg, the final height minus the initial height, and plus half m, the final velocity squared minus the initial velocity squared. Let's sub in now. So we know friction was 20. Delta x. So delta x is the actual length of the path taken. So in this case, they're referring to the length of RS. We don't know RS, so let's just leave it as RS. So RS and then cos of 180. Because remember, the object is moving up the slope, but friction is acting down the slope. So there's 180 degrees between them. That's going to equal, we know the mass is 20, 9,8. The object, the final height of the object is 4 meters above the ground. The initial height of the object at the beginning of the slope was 0. Plus half of 20. It stops at the top of the slope, right? Comes to rest at point S, yes, so it stops. So it's going to be 0 squared minus, and the velocity at R, so we worked it out, it was 9,9. So now it's just a matter of solving for RS. And we'll solve for RS, we'll get RS is equal to, double check, 9,81. Okay, so now we can use trig and work at the angle. So if I draw a triangle here, we worked out that this is 9,81. We've been given the height is 4, that's theta, that's 90 degrees. We want theta, so we can use opposite hypotenuse, we can use sine. So we'll say sine of theta is equal to 4 over 9,81. We can solve for theta, and theta will be 24,06 degrees. Okay. Let's move on. Question 5.2. At a construction site, a 100 kilogram block is lifted upward at constant speed of 0,1 meters per second by a crane, as shown in the diagram below. Define power. Again, definitions, you have them, so just learn it. 5.2.2, calculate the average power dissipated by the crane while lifting the block upward. So they want average power. So that if you go to your data sheet, you'll find the formula for average power. The formula for average power, P average, is equal to F times V average. Okay? They tell us that it's moving at a constant speed. So it's not changing, right? So V average is going to be 0,1. Right? They tell us it's 0,1 meters per second. Now we need to figure out the force. So let's quickly just draw a free body diagram. It's being pulled up, so that's the force applied. And then there's the force of gravity that's pulling it down. Now, since they tell us it's a constant speed, right? It means that acceleration is 0. It means that F net is equal to 0, which tells me that Fa is equal to Fg. So this force, the pulling force, the force applied, is going to be equal to Fg. So I can say that the power average is equal to 100 times 9,8 times 0,1. And the average power is going to be 98 watts. Not too bad. Okay? If you learned something, or you want a specific paper to be done, or if you just generally enjoyed the video, let me know below that thumbs up button. I'll see you in the next video. Bye-bye.